I remember when I was in school, we had to memorize in geometry the diagonals of certain quadrilaterals, like a rectangle. For example, the diagonals of a rectangle are going to be equal. So the idea is if we take a rectangle and we look at the diagonals, these are equal. And so I wondered, why? I don't even think I wondered I wondered at the time, why did we have to do this? But I never wondered, like, why are they approaching it this way? What does this have to do with anything? And it really had to do with the fact that we used the compass for pretty much everything when we would build geometric shapes and design, from a cathedral to, making a ship or navigating the ocean, constructing a house. So you would use these tools to build shapes. And so there is a very good purpose of why we would look at the diagonals. So let's take a look first. If we draw a circle and we go across through the middle, that's the diameter. So we're going to use one circle. And we want to build another diameter. So we'll know it's implied then that this and this are equal. So we're going to make two equal lengths. We'll use our compass to bisect it. So I'm going to open it a bit, make my perpendicular bisector. And so then I'm going to draw the line. And now we have two equal lines that are cut at 90 degrees, a perpendicular bisector that's even. And so one of the reasons we do that is because we can build a square this way. So that was something we learned about the property of the diagonals of a square. Like, who cares about the inside of a square? Well, it's because that's how we built it. And so I want to take some time to go and look through the quadrilaterals and how we build them. And for me, it gives you a different perspective. So, right, instead of the perspective of, oh, we're going to draw a square and the sides are equal. Well, we're looking at the perspective of, how did we use a compass to build them? And again, it's giving you a different point of view. Instead of focusing on the outside and the angles, we're focusing on creating them and doing that from the inside. So I just think it's good perspective. So let's do something similar here. Only now let's use concentric circles. So we'll make one circle smaller. We'll make one circle bigger. So it's a circle and a circle with the same center. That's called a concentric circle. So I'm going to do the same thing and do diameter across. So from here to here and here to here, we have the diameter. And this time we're going to perpendicular bisect it. Only we will stop at the smaller circle. So instead of what we just did with a square and go straight up to make another, you are going to stop and make the perpendicular line on the edges of the smaller circle. So what shape is this going to make? Can you see it? And so a squared plus b squared equals c squared, these are the same here and here. It means that that line that's green will equal this line, and this small radius and the large radius, and this is the small and the large, right? Also have to, by the Pythagorean theorem, a squared plus b squared equals c squared, will prove that these lines are all the same. And we have what we might call a diamond or a rhombus. So we have a square, which is obviously these are quadrilaterals, meaning four sides. But the word square is from the word quad, the root word in Latin, so it means square. Rhombus is actually the root or the word for a top. So it's a word that means top. When you imagine spinning this, it's actually going to get 3D. You spin it, and it'll make a type of a top. And so let's take a look at what happens. What happens if we change this circle? It'll get, these will squeeze together, and if we get it to be smaller than the circle in the center, then it goes from being wide to then being skinny, right? So it would look more like this. So we can see that based on the size of the circle on the inside, we will change the dimensions of the rhombus. So let's do this here. Oops, I think I missed the center here. Get it quite right. Let me redo that. So now instead we have a larger circle. So let me use a different color. Maybe I'll use orange. And now from here to here, right, my rhombus is going to get a little bit taller. Or if I make a very small circle, I'll just freehand this one. I'll use purple here. Oh no, I actually won't freehand it. I'll use my ruler. Won't take that long. And so you see, based on this circle, you're going to get taller or shorter, and you can even make it longer. You can keep going. If I extended it further, right, it's going to get taller and skinnier. So the dimensions will change with the type of circles that we have here. So let's say we go here, right? Suddenly our rhombus is tall and skinny, or our top. So to make a rhombus, one of the definitions is it has perpendicular lines in the center, like these do. So this is technically a rhombus. It's in the rhombus family. You have two concentric circles and you perpendicular bisect them. And the longer the lines are, if you make them longer, it'll get wider. Make them shorter, they'll get skinnier. And so you can adjust the size of your rhombus. So with those two constructions, we use the perpendicular bisector. What happens if we don't? So let's do a circle. I'll get this one ready over here. Make some concentric circles again. So what happens if we don't use the perpendicular bisector? If we don't use the perpendicular bisector, I'm still going to do the same idea here. We drew a line through the center, and then we perpendicular bisected it. It made a square. What if it doesn't? So let me just go through the center and bisect it, cut it in half, but not make 90. No perpendicular. What are we going to get here? Well, if we go around the edges, we're going to have a rectangle. And you see this rectangle, very short and very wide. Now, obviously, when we make regular constructions, we want to be more careful. But you see, we have a rectangle. So then again, we have the rectangle. I believe it's rectus in Latin. It has to do with a right angle. And that's what a rectangle has, is 4 right angles. Well, how do we build it? Why did we have to study when I was in school that the 2 diagonals are equal? Because that'll make a rectangle. So what happens if I take the first line and I change the direction? Now the rectangle is going to change shape. So let me go here. Marker. This color. And so you see the rectangle went from skinnier to taller. So if you think of 2 markers, where did I put my cap? If you take 2 diameters, you're going to get a rounded rectangle. So you could make it very tall and very skinny. You can make it, medium, then it'd be a square. They're exactly even, so that's a square is in the rectangle family. Or instead of being skinny, we could do what we started with, very wide, very short. So simply by changing the 2 diameters, you'll have different sizes of rectangle. Now, what happens if they're concentric circles that we use? So now what happens if we have, instead of going all the way through like we did in the first page, the second example we did, we have 1 diameter of a large circle, then we bisected it, right, and we made a rhombus. So what happens when the rhombus isn't 90 degrees and it's bisected at any other angle? What shape is that going to make? Can you see it? And so, if you haven't seen it or noticed it yet, you see these are 2 parallel lines. 2 are parallel lines. So we have a parallelogram. And so this is the same line with the same slope. So compared to this line, right, we have 2 congruent angles. These are vertical angles here. All of them will have vertical angles across from each other, but here and here we have equal angles, and here we have equal angles. We have a parallelogram. So when you take a larger and a smaller diagonal that go through the center and bisect each other, we have a parallelogram. But what happens if you take that parallelogram and you move the smaller side maybe this way? Well, the parallelogram is going to change, and now it's getting a little wider. And if we did make it exactly 90, right, a little bit more, it would be a rhombus. But as of now, this one's shorter, this one's longer. So if you maybe think of this toothpick and think of cleaner here, the little type of Q-tip and a toothpick, right? 90 degrees is a rhombus. And if we start to change it, it's going to make a very, very short parallelogram, longer, 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 longer. Or you move this one, suddenly the parallelogram will get taller and skinnier. So what if we use concentric circles? And start with the line here. And we make something parallel. So through here parallel, or up here parallel. What's going to happen? So let's, I guess, practice the construction for a parallel line. So the construction for a parallel line, you can fast forward if you don't want to see it. We'll start here. We'll draw an arc through the angle. Let's say I want to spot. Let's say I want to start there. I will do the same arc. And then I'll measure how wide open the angle is. So it's from here to here, or I could turn it around and test it. If I were doing a real construction, I would obviously be more careful and precise. We're going for speed here, so now we can see that's how wide the angle is at that arc. This distance, that's how wide open it is. So that's the same distance. We'll check how wide open it should be. So now we have here a line. Now, since the circle here is curving, this line is getting smaller the further up you go, right? So this line up here, we can test it, is shorter from edge to edge of the circle. So from here to here, it's shorter. Here to here, it's longer. We can check that. Our compass as a measuring device. That's how long the diameter is, and it should be that long. So right, this line is that much shorter on top. So why did we do this? Well, now that we have parallel here and here, here to here, shorter, we have a trapezoid. Right? So the trapezoid has the definition. We're running out of ink here. Or the root word, the meaning of the word trapezoid is a table. You can imagine a table this and the ground. That'll make a trapezoid. But then you could turn it around. I believe I've seen tables shaped like this in videos or pictures from Egypt. I forgot to make the vase. So we have a table. And so what happens if we had made it up here parallel? Right? The trapezoid would have a skinnier base on top. And what happened if I used one of the smaller circles? I could make a circle any size. Well, we could make a trapezoid from here to here, right? It'll have estimate it. It'll have smaller angles. It'll kind of collapse in. The type of trapezoid this is an isosceles. If you imagine an isosceles triangle where two sides are the same and you chop off the top, isosceles means equal legs. That's what the root words are. Iso is to be the same, and celes is referring to the legs because these are considered two legs. The bottom is considered the base. So these are equal. This is an isosceles trapezoid. How do we make it a non-isosceles? Well, if this side here stays the same and we change where we meet on the top. So you see here now it's no longer isosceles. I can go to any spot and change it, and we don't necessarily need to keep it isosceles. So a trapezoid can use concentric circles. Really, a trapezoid can just use one circle. But if you make a concentric circle, it'll help you keep it isosceles, and it'll help you to make it shorter and have smaller base angles. So a trapezoid, we learn when it was isosceles, the two diagonals are the same. And when it's not isosceles, like the brown one here, the two sides are different, the two diagonals. So we just have, one or two more ideas. One idea is if we just keep it connected in here, we'll have a quadrilateral. If I pick the points randomly, quadrilateral will not be even, right? It'll just be 4 sides. It won't be a square, it won't be a rectangle. I can pick it any spot here, and as long as we connect the 4 sides, we're clearly going to get a quadrilateral, something with 4 sides. And we could even check out the angles. So why do the opposite angles equal 180? So why is here and here, why are they supplementary? Why do they add up to 180? Well, it's because this bottom one uses this much of the arc, and then this one's cutting off the rest. So they're both cutting off and using the arc of the entire circle. And then we learn that the angles are half the arc. So together, they make the whole circle of 360. So together, the angles are half of 360. So these two must be 180. So quadrilateral. And the last shape is when you use concentric circles. And you perpendicular bisect once again. I will draw my diameter. Bisect it or cut it in half with the perpendicular line. So perpendicular bisector. We'll both cut it in half while at the same time making 90. Move my compass there, had to fix it. And again, if we were doing real work here, we would be more careful and do this slowly. So now we have two concentric circles. If we connected these, they're 2 diameters, so this would make our square. What we can do with this is we can see a few things. So when we have a square, it helps us, we said, understand that the diagonals of a square are perpendicular. If it was a rhombus, so we can go here where the sides are equal, we also see that a rhombus has perpendicular lines. How do we make a different shape? Well, we could move along this line here. So let's pick a spot. Let's pick down here. If I connect the edges, I'm going to have a kite. And so if I move this higher, the 2 legs on top will be closer in length to the 2 legs on the bottom. If I go down lower, it's going to make the 2 legs shorter. So we have different types of kites or tops. This one here reminds me of a top, but the word top, I shouldn't reference it. The word top has more to do with the word rhombus. That means top. So a kite, we can use a bigger circle and a smaller circle, bigger line and then a smaller line. The definitions of the diagonals of a perpendicular line is they make a T or a cross. They make perpendicular lines. So, a kite has other shapes that we think of in its family. The square shape is in the kite family, and the rhombus is in the kite family. So they are technically kites. But you can see sort of why when I was in school we had to memorize what the diagonals were doing. So the diagonals of a kite are perpendicular. They make 90. And typically one is shorter. They cut each other in half. These two are shorter. These are not always the same. So this one up here, it could be shorter, this one longer. But if it is a rhombus, then these two are the same. These two are the same, and they're all congruent to each other if they're square. If they're square, diagonals make 90, but they're all equal. It's just a rhombus. These two, these two are shorter, these two are longer. That's what we have with a kite.